Hello everyone, my name is Raúl Omar Escamilla Guevara and I am a student at the Instituto Politécnico Nacional. Today I will talk about our study on the gadolinium-0.5 lithium-0.5 titanium oxygen-3 perovskite. We focus on how substituting gadolinium atoms with lithium atoms change its structural and electronic properties using density functional theory or DFT. Perovskite rare earth titanates are interesting because of their high photoluminescence efficiency, tunable bandgap, and high charge carrier mobility. Gadolinium titanium oxygen-3 (GTO), for example, has an orthorhombic structure, a Pbnm space group, a bandgap of 1.8 electron volts, and ferromagnetic behavior. Our goal was to see how replacing gadolinium with lithium could improve its properties for possible lithium-ion battery applications. To study this, we performed first principles DFT calculations using the custom code. The parameters were a 665 K-point mesh, a 550 electron volt energy cutoff, a Hubbard U value of 4.5 electron volts for titanium atoms, and ultra-soft pseudopotentials. We investigate three substitution models: lamellar, columnar, and rock salt. In addition, we analyzed the density of state to understand the impact of lithium at different crystallographic positions. As you can see here, Figure 2 shows the side view of the GTO perovskite and the three substitution models. Green spheres represent lithium atoms, while purple spheres represent gadolinium atoms. Now, moving on to Figure 3, here we can see the 4 octahedral sites and the 6 relevant bond lengths in each octahedron. This is key for quantifying the octahedral distortion caused by lithium substitution. In Table 1, we compare structural properties, including lattice parameters, cells volume, and average distortion, for each substitution model. For reference, we also included results from hybrid functional calculations, experimental data, and the pristine compound. Now let's look at Figure 4, which shows the band structures of the three models alongside the pristine GTO. From these results, we can highlight three main conclusions. The first one, the columnar model has the smallest octahedral distortion and the smallest unit cell volume, even smaller than the pristine GTO. The second one, the bandgap increased significantly, about 92.8% for lamellar, 47.3% for columnar, and 78.1% for rock salt. And finally, in all models, the density of state shifts to more positive energies. In the conduction band, the most intense states come from titanium 3D and gadolinium 4F orbitals. In the valence band, they come from oxygen 2P and gadolinium 4F orbitals. In summary, lithium substitution in gadolinium titanium oxygen-3 significantly modifies both in structural and electronic properties, potentially making it more susceptible for lithium-ion battery applications. Thanks for your attention. This work was partially supported by the project IPNSIP and the UNAM Gd0.5Li0.5TiO3 program. Escamilla and Lopez Aranda acknowledge the scholarship granted by CECITI and BEIFI-IPN. Cervantes acknowledged the postdoctoral scholarship granted by CECITI. Muñoz acknowledged the postdoctoral scholarship granted by the Pbnm. Thank you.